It's Shannon Matchick-Myers. I hope all is well with you. Today we will be looking at arguments with quantified statements. So enjoy. First off, let's talk about the rule of universal instantiation. If some property is true of everything in a set, then it is true of any particular thing in the set, all right? So universal instantiation, is the fundamental tool of deductive reasoning. Below, we have a couple of universal truths we know from algebra. For any x belonging to the real numbers, x not equal to 0, and integers m and n, sorry, I've got an extra comma here, and integers m and n, x raised to the m minus n is equal to, it's a little backwards from what you're used to, x to the m divided by x to the n. And for any x belonging to the real numbers, x not equal to 0, x to the 0 is equal to, beautiful, 1. Now let's think about how we'd use universal instantiation to simplify r to the negative k, where r is a particular non-zero real number and k is an integer. So our very first step would be to take a look at what? Good. R to the negative k is equal to, awesome, r to the 0 minus k. This reasoning isn't fancy. It's just basic algebra, right? So that's all we'll put for that one. Now, our next line would be utilizing that first bullet point, which is r to the 0 divided by r to the k. And so what is this reasoning? For all real numbers, x, and integers m and n, x raised to the m minus n is equal to x to the m divided by x to the n. Now that is a universal truth. Okay, so we've established this universal truth, but we're not dealing with x's, m's, and n's, are we? We're dealing with r, 0, and k. So let's take a look. R is a particular real number, and 0 and k are particular integers. All right, that kind of part of it is we're looking at a particular instance. So we go from a universal truth and we apply this particular, a particular instance to that universal truth. All right, and then we using, what is this here that we're utilizing for our conclusion? We're utilizing that, therefore, r raised to the 0 minus k is equal to r to the 0 over r to the k. And that's the conclusion for that particular piece. Good so far? All right. Next piece, well, this is equal to 1 over r to the k. So what's our universal truth? Our universal truth for all real numbers x, x to the 0 is equal to 1. So r is a particular real number. And remember we said that r was non-zero, so we won't get a 0 to the 0 situation. Therefore, r to the 0 over r to the k is 1 over r to the k. So here, this was the first statement was our universal truth. And then we had our particular instance. And then we have our conclusion. Good so far? Awesome. All right, so now guess what? Remember the modus ponens for arguments, valid arguments. So we're going to take a look at universal modus ponens. So the formal version would be for any x, if p of x, so we're using predicates, then q of x. So what does this mean informally? If x makes p of x true, then x makes q of x true. All right, well, universal modus ponens, our next step is, remember, you assume the given part, right? The p of x, but we're going to say p of a for a particular a. We're going to say a makes p of x true. Well, therefore, q of a. So if a makes p of x true, therefore, and these are all the statements, therefore a makes q of x true as well. All right, let's look at an example, a couple of examples. So here, let the following law of algebra be the first statement of an argument. For all real numbers a and b, a plus b, the quantity squared, equals a squared plus 2ab plus b squared. Suppose each of the following statements is in turn the second statement of the argument. Use your universal instantiation, or universal modus ponens to write the conclusion that follows in each case. So remember, this one here is the first line, all right? The second line for number 1, a equals x and b equals y are particular real numbers. So what is our conclusion? Therefore, beautiful, x plus y squared would equal to x squared plus 2xy plus y squared. Cool so far? Awesome. Very good. All right, so now let's take a look at our next problem. And the next one deals with a equals g at r and b equals g at s are particular real numbers. And so we want to, that's the second line of the statement. So we want to do what? Therefore, good. G at r plus g at s, the quantity squared, would equal to g at r squared plus 2 times g at r times g at s plus g at s, the quantity squared. How's it going so far? Good, good. Alrighty, so now let's take a look at number 3. Now we've got a equal to log at t sub 1 and b equal to log at t sub 2. So now what do you think? What should we get for that? Very good. We would have log at t1 plus log at t2, the quantity squared equals log at t1 squared plus 2 times log at t1 times log at t2. And then wrapping it up with quantity log at t2 squared. Good so far? Awesome. All right, and then we'll put our period to show that's the end of the statement. Now, let's check out example 2. Use universal instantiation, or universal modus ponens to fill in valid conclusions for the following argument. For any real numbers, r, a, and b, if r is greater than 0, then quantity r to the a raised to the b is equal to r raised to the a times b. So that's the first statement, the first argument. Remember, what was that called? That was called the major premise. All right, the minor premise is this next one. R equals 3, A equals 1/2, B equals 6 are particular real numbers such that R is positive, right? Therefore, what would we say? Beautiful. 3 to the 1/2 raised to the 6 is equal to 3 raised to the 1/2 times 6. Awesome. All right, now, of course, if there's universal modus ponens, there needs to be universal modus tollens. So the formal version, remember with modus tollens, you negate your q of x. You negate your q of x. So for any x, if p of x, then q of x. So then we would say not q of a for some particular a, so negating that second predicate, and we would say therefore not p of a. Informally, if x makes p of x true, then x makes q of x true. A does not make q of x true. Therefore, A does not make p of x true. Good, good? All right. So, more examples using modus tollens. We want to make our statement so that we've used our conclusion makes it a modus tollens argument. So if a computer program is correct, then the compilation of the program does not produce error messages. Compilation of this program produces error messages. Therefore, so it's kind of weird, it negated a negative, which somebody I think asked me about this, so my apologies for not getting back sooner, but that's okay. The point being is that the second predicate was negated, and so we would say therefore what was that first predicate? It's about the computer program being correct, right? So we would conclude that therefore the computer program is not correct. Okay? All right, so now a definition. We've had somewhat of a definition like this, but now it's involving predicates. So to say that an argument form is valid means the following. No matter what particular predicates are substituted for the predicate symbols in its premises, if the resulting premise statements are all true, then the conclusion is also true. an argument is called valid if and only if its good form is valid. So let's talk about how we can use diagrams to test for validity. All right, so this is kind of cool, and I will have this on the exam, so make sure you know how to do this. So here, first of all, we'll just look at a statement. It's not a whole, it's not a whole argument. It's just a statement. So here, for any rational numbers x belongs to the real numbers. So this is saying, remember, if x is a rational number, then x belongs to the set of real numbers. All right, well, you can make a circle. So here we've got this circle in black, and I'll call this one. So basically, if x is true for P, then x is true for Q. So this is basically the big set, after the then statement here, is the set of real numbers. And then inside, what we're doing is we are putting in another circle, right? Because every rational number is a real number as well. So here, if we put in another circle, so every single rational number is in the set of real numbers. So the diagram would look like this. And this is just one statement, right? Not a whole argument. So now let's kind of continue this thought, right? Then let's go back to our favorite example with red. So let's look at these arguments here. All tigers are felines. Red is a tiger, therefore red is a feline. So this first statement, remember, is the major premise. Okay, all tigers are felines. So felines would be the biggest group, right? This is saying if X is a tiger, then X is a feline. So felines would be the most outside. And then if we go and add in, another circle here, tigers. Now we're talking about, so this is our, over here, this is our major premise, the first line. Okay, so if we then take a look at that second line, red is a tiger. Well, so remember this means tigers, and red is part of that group. So we'll say this here is red. If you put them together, the major and minor premises, let's see what we have. We have our result of, okay, so here we have the felines and the tigers. Let me get these out of the way. But what has to go in here, remember red was inside the tigers. And so this would be a valid argument, because putting these together, you've got this one circle where they're all part of each other. Now let's look at something that maybe won't work out so well. So here again we have all tigers or felines. So wouldn't it wouldn't it really be the same initial figure, right? So this again is our major premise. Now our minor premise says red is a feline. Okay. And red is a feline. Over here is what that second statement says. So the second premise, the minor premise rather, is that red is a feline. But what happens here is that you get two situations, don't you, that are possible. So you get two possibilities. Red could be a feline which is not a tiger, like a house cat, which he really is, or red could be a tiger, right? So there's two cases here, two possible conclusions. So this is not valid. And this happens to be a certain kind of error. Do you remember? This is an invalid argument. And it is assuming what you're trying to prove, which is a converse error. The first one was a valid argument. And this valid argument was using what? Beautiful. Modus, ponens. All right. So let's take a look at, the official converse and inverse errors. So we've done an example of a converse error. And let me draw a line here so you can see where the two problems separated. All right, so here the formal version would be for any x, if p of x, then q of x, q of a for some particular a, therefore p of a. Remember, this is an error. So informally, it's saying if x makes p of x true, then x makes q of x true. A makes q of x true. Therefore, A makes p of x true. Now, if you have an if and only if, it will work, right? Because, and we'll get more into that. We're going to be doing more proofs, learning all kinds of cool techniques in chapter 4. But it's not always true. All right, let's look at our favorite example on red. I'll just draw a freehand this time. See how good my circles are. So you have, again, felines. All tigers are felines. And then we have the tigers in here, right? And this is our major premise. Our minor premise is that red is not a tiger. So again, we have tigers. And red's outside of that. So we're going to put him outside the tiger circle. Now, what are the possibilities here? I mean, can you assume that red is not a feline? No, I mean, I think, again, you would get two cases here, right? you know red's not a tiger. So red will never be in the tiger circle, but he could be a feline. In fact, he is. He's a house cat. But if we didn't know that, he might not be a feline. So he could be a feline, which is not a tiger. Or he might be a dog. He might not be a feline at all. All right. So again, we have these, two possible conclusions, which means that the argument is invalid. And this error is inverse error. Okay, so formally, the inverse error says for any x, if p of x, then q of x, this starts out the same, not p of a for a particular a, therefore not q of a. And again, this is an error. This is not true necessarily. So if x makes p of x true, then x makes q of x true. A does not make p of x true. Therefore, A does not make q of x true. So let's take a look at example 4, and again we'll use our diagrams. Those are a good way to kind of take these arguments apart and see if they're valid or invalid. All right, so all honest people pay their taxes. And what is this saying? It's basically saying what? If you're an honest person, then you pay your taxes. So our outside circle would be pays taxes. Inside circle would be honest. And this one is which premise? Good, our major premise. All right, Clyde is not honest, so this is our minor premise. All right, so here we have honest, and Clyde is outside of honest. I picked Clyde because of Bonnie and Clyde, the bank robbers, right? All right, so that one, of course, is our minor premise. So what do you think? I mean, is this valid? Like, what could happen? I mean, you could have a criminal who pays their taxes, right? You could be a bank robber and pay taxes. Or you could be a criminal who doesn't pay taxes. Or so maybe a person who's not honest and who doesn't pay taxes. So again, we end up with these two cases. And all we know for sure is that Clyde is not honest. So Clyde could be honest and but pays his taxes. Or Clyde could not be honest and not pay his taxes, right? Or no, so it's two, again, you have two situations that could happen, right? Two possible outcomes. So what does that mean? That means we have an invalid argument. And what kind of error is this? Beautiful. It's an inverse error. Okay, now let's take a look. Oh, look at all that room I allowed myself. Let's take a look at number 2. For all students X, if X studies discrete math, then X is good at logic. Saul studies discrete math, therefore Saul is good at logic. So let's see what we have going on. So our big circle would be what? Very good. Good at logic. And our smaller circle would be studies discrete math. And this is which premise? Awesome, our major premise. Okay, minor premise. Saul studies discrete math. So Saul is inside here. So what do you think? Beautiful. The only conclusion you can reach is that Saul must be good at logic. Oops. Because Saul is part of the group that studies discrete math, and every student who studies discrete math is good at logic, right? So there's just one conclusion, one possibility. So this is a valid argument. And what kind of form does it use? Beautiful. Modus, ponens. All right. The very last thing we'll go over is universal transitivity. So the formal version is for any x, P of x implies Q of x. For any x, Q of x implies R of x. For any x, therefore, for any x, P of x also implies R of x. So any x that makes P of x true makes Q of x true. Any x that makes Q of x true makes R of x true. Therefore, any x that makes P of x true makes R of x true. And that's all we have for today. So I hope you have a wonderful evening or morning or afternoon whenever you're watching this. And if you like the videos, please subscribe and let me know what else I can do to help you. Have a wonderful day. Bye.